In question number 11, the half-life of a radioactive element X is half of mean life of radioactive element Y. If initially both of them have same number of radioactive atoms, then we have to check the validity of these statements. So it is given in the question, T half of X is equal to half of mean life of radioactive element Y. So mean life will be 1 by lambda Y. So if I multiply it by ln2 and divide by ln2, it can be written as ln2 divided by lambda Y is equal to T half of Y, and this is divided by 2 ln2. So 2 ln2 is greater than 1, so it means T half of X is less than T half of Y. So if half-life of X is less as compared to the half-life of Y, it means that the decay rate of X is greater than the decay rate of Y. So option 4 is the correct answer. Let's move to question number 12. In question number 12, a Li plus 2 ion and a Be plus 3 ion are in first and second excited states respectively. If L of Li and L of Be are their respective electronic angular momenta, and E of Li and E of Be their respective total energies, then we have to compare them. So here we have Be plus 3 and here we have Li plus 2. So Li plus 2 is in first excited state, so N is equal to 2, and Be plus 3 is in second excited state, so the value of N is equal to 3. The value of Z for Be is 4 and the value of Z for Li is 3. So if I take the angular momentum L, that is equal to NH upon 2 pi. So L is proportional to N. So the N of Be plus 3 is more. So the angular momentum of Be plus 3 is greater than the angular momentum of Li plus 2. If I consider the total energy, then total energy is proportional to Z square by N square if I considered their magnitude. So the value of N and Z are known of Li plus 2 and Be plus 3. So on comparison, we will find that the E of Li plus 2 is greater than the E of Be plus 3. So here we are comparing their magnitude. So if I check the options, then option 3 is the correct answer. Let's move to question number 13. In question number 13, a nucleus at rest undergoes alpha decay emitting an alpha particle of mass m alpha and de Broglie wavelength lambda. If mass of daughter nucleus is 57 m alpha, then the total kinetic energy produced in the decay. We know that the total kinetic energy produced in the decay is equal to the Q value of the process. So this is equal to, so if I consider this as my nucleus and it undergoes an alpha decay, suppose this is alpha particle, so the mass is m alpha and it is moving with velocity v1. So applying the principle of conservation of linear momentum, the daughter nucleus will move in this direction. The mass of this daughter nucleus is 57 m alpha and it is moving left with velocity v2. So from the principle of conservation of linear momentum, we can say that m alpha into v1 is equal to 57 m alpha into v2. So the value of v2 comes out to be v1 by 57. So if I write the Q value or the total kinetic energy produced in the decay, this is equal to half m alpha into v1 ka square plus half 57 m alpha into v2 ka square, and v2 we have already calculated, v1 by 57 whole square. So if I solve this, it comes out to be half m alpha into v1 ka square into 1 plus 1 by 57. So it comes out to be 58 by 57 and divided by 2. So it is 29 divided by 57 into m alpha. So I can write in this way, m alpha into v1 whole square divided by m alpha, and we know this is equal to h by lambda. So if I write this is also equal to 29 by 57 h square upon lambda square m alpha. So option 2 is the correct answer. Let's move to question number 14. In question number 14, if the maximum and minimum voltage of an AM wave are x and y respectively, then modulation index is given by. So suppose this is the carrier wave and this is the amplitude of the signal. So this is AM and let the amplitude of this is AC. So the maximum voltage of an AM wave is AC plus AM and the minimum voltage is AC minus AM. It is given in the question equal to x upon y. So if I apply componendo and dividendo, the value of AC upon AM comes out to be x plus y divided by x minus y. But we have to calculate the modulation index. So the modulation index is given by AM by AC. So it is equal to x minus y divided by x plus y. So option 3 is the correct answer. Let's move to question number 15. In question number 15, in a common emitter amplifier, the voltage across a load resistance of 2 kilo ohm is 4 volt. If base resistance is 1 kilo ohm and power gain is 200, then the input voltage and base current respectively are. So in case of common emitter amplifier, we know that power gain is equal to beta square into load resistance RL divided by RB, that is base resistance. So if I substitute the data, so 200 is equal to beta square into 2 by 1. So from here we get the value of beta. Beta comes out to be 10. So voltage gain, output voltage divided by input voltage is equal to beta into RL upon RB, and we have to calculate the value of input voltage. So output voltage is 4 divided by V input is equal to beta, that is 10 into 2 by 1. So from here the input voltage comes out to be 0.2 volt. So the base current IB is equal to input voltage, that is 0.2 volt divided by base resistance, and it is given 1 kilo ohm. So it comes out to be 0.2 milliampere. So option 4 is the correct answer. Let's move to question number 16.